All right, to finalize this chapter, we need to cover two more topics. One is related to dependent motion and the other is related to relative motion. So think about that Atwood machine that we looked at in General Physics 1. When that machine, we had two masses tied together. They were physically connected by a rope or a cable. And we knew that if mass 1 went down like this, then mass 2 had to go up because they were physically tied together. And we saw it in numerous situations. So I had a block on the desktop and I had a block that's hanging off. If that mass was heavy enough, we would get this motion to go there. So mass 1 would move down and mass 2 would move off to the right. This is what we refer to as absolute dependent motion. It's the motion of each mass or particle is dependent or is tied to the other particle. So when we do this, we can look at how these particles are together. And so let's look at this situation that comes up in our book where we're looking at the length of this rope and the length of this rope. Now we can kind of disregard the length of this part over here because that's going to be constant no matter what we are doing in this situation. So we're going to worry about our S of A and our S of B. So let's kind of move on here for a second and go to the next slide. And so we know that each box can be related mathematically by defining some position coordinates or lengths of the rope in this case. And each coordinate axis is defined from a fixed point or a line. And we'll see how that's going to come into play when we work an example where we're only going to work with that line. Since the chord is fixed length, we can relate those positions. So I can look at the total length of the chord. It's the length of S of A plus this little bit that goes over C and D and the length of SB. But when we deal with the length of CD, a lot of times that's going to be constant throughout our system and it's really not going to change. So we don't necessarily have to look at that. And that makes it an easier way to handle the material. So if the chord's got that fixed length, we can look at that total. And we know that if we do a change in the lengths, that fixed length is there, so it's not going to change over time. So it's going to go to 0, and we can look at the velocity. And just like in our Atwood's machine, if I had a mass that was falling, the other one had to be going up. They were going to have the same velocities, but they're going to be traveling in opposite directions. And you can do the exact same analysis and find that for acceleration. So when we work these problems, what we want to do is we want to really draw our picture and think about what the dependent motion is going to be. So we want to define our positions. We want to relate those positions and don't worry about the segments of the chord that don't change because we can leave those out. And then we want to be able to write separate equations for each one. And we need to make sure that we keep track of our signs. And you'll see that in the two examples which we're about to do. So in this first example, this happens to be problem 199 in the textbook, and we've got a truck that's going to be pulling a log towards a tree. And we're going to use a pulley system. And so we want to know how far the log moves if the truck moves 4 feet. So we want to look at the segment. So that's exactly what we have to do is we have to break this up and we have to look at our segments. So if we define from the center of our pulley as SB and the section that's going to change related to the pull as SC, we can look at the total length of the rope as 2SB because we've got the two parts around the pulley, and then the section of the rope that's SB minus SC. So we've got our 3 sections of the rope. Again, if we're going to do the change with respect to time, the change in the length of the rope isn't going to change. So we know that that's got to equal 0. So it's going to be 3 times the change of SB and minus 1 of the change of SC. And if we know that we've pulled the change of SC is 4 feet, we can go through this and we know that we're going to move this log 1.33 feet in that direction. Now, again, you can have it play with how the signs are going to come into play and look at it. So you've got to kind of make sure you understand how you've put your signs into your equation based on the question that you're being asked in the homework, how you've set up your problem, and how you anticipate the motion to go. So those are the kinds of things you really have to stop and think about what's physically happening in order to do this. So now let's look at that datum picture. So I've got a pretty complicated system here. I've got a device that's going to curl or are going to pull on rope A, and we want to move this load up. So if you look at how this cord is, this cord goes from here to here, then this one is attached from here to here, and this one is attached from there to there. Now, one of the things we didn't talk about in general physics, but in a lot of general physics texts there are, and as we start into getting to engineering, we talk about mechanical advantage. And having these pulleys really relates to that mechanical advantage, which is one of the reasons why we use pulley systems. So we're given this system, and we want to determine the constant speed of which cable A must be drawn by the motor to hoist up this load 6 meters in 1.5 seconds. So we want to know what we're going to do to achieve a velocity of the load going up 6 meters in 1.5 seconds. We can calculate the magnitude of our velocity. We know that that's going to be 4 meters per second. But now we've got to kind of analyze the system in order to see what we want to have happen. So again, because we're using this as our reference point, that's how I've kind of drawn this. And I've drawn my segments of the rope. So this is going to be SD, this is going to be SC, this is going to be SB, and here's my SA, and we're looking at the velocity of A. So let's look at the length of rope 1. And it's kind of easier to go backwards. So we're going to look at the length of this rope. It's SB plus the length of SB minus SC, because remember, this part is that segment that's not going to change because it's going around the pulley. So I've got my length of rope 1. Now let's look at the length of rope 2. So this time I've got my SC, and now I got to take it into account of SD. So I've got my SC plus SC minus SD. And then finally, when I'm looking at the length of the rope around this pulley, I end up with 2 SDs plus the length SA. So we're going to clean this up a little bit. So I get 2 SB minus SC, I get 2 SC minus SD, and I get 2 SD plus SA. And just like what I did with the log problem, we're going to look at the change. So the change in length of length of the rope 1 is 0. So if I look at that, well, guess what? With respect to time, this just ends up being the velocity of B. And this ends up being the velocity of C. So we can get the velocity of B in terms of velocity of C. We can do the same thing for the length 2, and we get velocity of C in terms of the velocity D. Finally, we do it for the third length, and we've got the velocity of A related to the velocity of D. But we really want A in terms of B, so we're going to go step through. I'm going to start here, and I'm going to switch my negative sign over to there. So the velocity of A, which we know is going to be going down, which is why I've got my arrow going down, and I've got negative 2 VD. All right, so we know what VD is, right? It's 2 VC, and we know what VC is. It's 2 VB. I can plug that in. We know what we want to have, that velocity of VBB, and so we can put that in there, and we see that the velocity of A is going to be 32 meters per second, and we're pulling down on the rope. So that's how dependent motion is going to work. Well, the other type of motion where we're having to look at things is relative motion. So remember when we started talking way back when, and we talked about if I'm on a train and I'm walking towards the front of the train and then in the same direction as the train was going, my velocity to an observer on the ground would look like I am walking at the same speed as the train plus whatever it is I'm doing. Now, if I'm walking to the back of the car, I'm going the other direction, those two velocities would be subtracted. So that's our relative motion. So we're looking at the absolute position of our 2 points, and we're looking at whether I'm observing the motion of this particle B either having a person moving at the same time. Remember, think about Doppler effect when we have things that were moving at the same time, how it might change things. And then if I have something with a fixed observer. So we've got two absolute points, A and B, and we're looking at how A is going to move with related to B. So we can do that in terms of position, and this isn't anything new. We're just kind of changing our nomenclature and kind of changing the symbolism that we're using. And we could do the same thing for velocity, right? We can do the same thing for velocity, and we could do the same thing for acceleration, because these are vector quantities and these are vector relationships. So we can actually do that and move on with that. And just as we've done before, a lot of times it makes a lot of sense to kind of look at our toolkit and then to look at some example problems. So one of the toolkits I want to remind you all about is the law of sines and cosines. Because when I'm dealing with relative velocities and I'm dealing with relative accelerations, you're dealing with those vectors and those vector quantities. We want to be able to utilize the easiest tools to make it work. So you want to just have a helpful reminder, and I've put that here for reference as you guys go through the material. Now you've got it kind of in your notes already, and you can work with that. So let's do a simple relative velocity problem. We've done a velocity problem like this before. I've got two airplanes, they're coming towards each other, and we want to find the velocity of B relative to the velocity of A. So the first thing we got to do is write out our vector. Well, this vector is going straight down. It's in the negative y direction. So I've got that plotted in there. And given our Cartesian coordinate system, if we say that this is only in the y direction, I can get my x and y components of this aircraft, and I can plug that into my vector notation, do my vector subtraction in this case, and calculate the overall magnitude and direction of the vector. Nothing really earth-shattering here. We've done these problems before, and just to kind of get us a handle on it. Now let's look at it from a different perspective. Let's look at it from a football player. We see these all the time. This is one of those things, and remember I've said in the past that you do more calculus and physics in your head than you'll ever be able to write down on a piece of paper. So one of the things we're going to do, this happens to be problem 12-233, and we've got a football player that's going to throw the ball. So we've got projectile motion, right? And we're going to make the assumption that both players are going to be this. So this is going to be a nice, where we start is where we finish kind of a problem. And so we're given the initial velocity and the angle of the ball. We're also at that same instant, player B is going to run to a position where he's going to attempt to catch the ball. And we want to know if player B can make it to that point C in time to catch the ball. Okay, we're not going to make that time exactly equal. Well, we're going to make the time exactly equal, but we're not going to adjust player B's velocity in order to have him be there at precisely that instant. We're just looking, could he get to that spot in time to catch the ball? So we know we've got some equations, and just like any projectile motion equation, we've done this before. I need the time that it's going to take, and I need the range that this is going to be. Now, because this isn't a constant acceleration, this happens to be gravity, and we're dealing in feet per second, we're going to use gravity as negative 32.2 feet per second squared. And we're still dealing with that special case that acceleration is a constant. And for throwing baseballs, throwing footballs, doing any of this kind of thing, that's exactly the situation we're going to experience. So we want player B to reach point C at least in time to catch the ball. Remember, we can do two equations, two unknowns. So I'm going to use the distance equation, and I'm going to use this velocity equation. I'm going to solve for time, and I'm going to be able to calculate the distance. So we can calculate that distance. Now we got to evaluate the motion of player B to see if he's going to make it there in time. So in this case, we're going to use the diagram here to help us determine the distance that he has to travel. And we're going to look at it in terms of his velocity. Is he traveling fast enough to get to point C. And if he's traveling, if his initial velocity of 23 feet per second, which is pretty fast running, okay? Now, granted, he's sprinting and we're only talking 30 feet, but still, that's a pretty big number. But we want to know if he does that, if he travels that fast, can he get to point C? So we're going to use our geometry to figure out the distance. He has to travel 55.96 feet. And he's got to do it in the time that we calculated up here. There's our time calculation. And so we know that he has to maintain a velocity of 20.8 feet per second in order to get to the point where, at point C, where he's in position to catch the ball. Now, of course, this is football, so he's not going to be able to just stand there and get it. But this is how we do those types of problems. Hopefully this kind of clears up some things for dependent motion and projectile motion, and we're getting ready to start chapter 13.